welcome to this problem walkthrough. Today, we'll be tackling problem number 1567, titled Maximum Length of Subarray with Positive Product. This problem challenges us to explore subarrays and identify the maximum length of those with a positive product. Let's dive in and explore the problem, its nuances, and the approaches to solving it. In this problem, we are tasked with finding the maximum length of a subarray within a given array of integers where the product of all its elements is positive. Remember, a subarray is a contiguous portion of the array, meaning the elements must appear consecutively in the original array. The goal is to determine the length of the longest subarray that meets this condition. For the input, we are provided with an integer array called nums, and the output is a single integer representing the maximum length of the desired subarray. Let's explore some examples to better understand the problem. In the first example, we are given the array 1, -2, -3, 4. The product of all the elements in this array is positive, calculated as 1 *2 *3 4 equals 24. Since the product is positive and the entire array is contiguous, the length of this subarray is 4. Thus, the output for this example is 4. In the second example, the array is 0, 1, -2, -3, -4. Here, the longest subarray with a positive product is -2, -3, -4, which has a product of -2 *3 4 equals -24. Although the product of these three numbers is negative, it is important to note that the correct subarray length is determined by the longest segment with a positive product, which happens to be 1, -2, -3. The length of that subarray is 3, so the output is 3. Now, let's consider a third example with the input array -1, -2, -3, 0, 1. In this case, the longest subarray with a positive product is -1, -2, where the product is -1 *2 equals 2. This gives us a length of 2 for the subarray. It's worth noting that while the subarray 1 also has a positive product, its length is shorter than the subarray -1, -2. This illustrates that we are looking for the maximum possible length. Additionally, the constraints for this problem specify that the length of the input array can be as large as 100,000, and the elements in the array can range between -10⁻9 and 10⁻9. This means we need to consider an efficient solution that can handle large inputs. When solving this problem, there are a few edge cases to keep in mind. First, if the array contains only positive numbers, the entire array will have a positive product, so the output is simply the length of the array. For example, if nums equals 1, 2, 3, 4, the output is 4. Second, if the array contains only one element, such as nums equals -1, and the number is negative, there is no valid subarray with a positive product, so the output is 0. Third, zeros in the array reset the subarray, as multiplication by 0 results in 0, which is neither positive nor negative. For instance, in the array 1, -2, 0, -3, -4, the longest subarray with a positive product is -3, -4, with a length of 2. Lastly, if the array alternates between positive and negative numbers, the solution must carefully track the product and its sign. For example, in nums equals -1, 2, -3, 4, the longest subarray is the entire array, with a length of 4. These edge cases highlight the importance of systematically analyzing the array for an efficient solution. To tackle the problem of finding the maximum length of a subarray with a positive product, one straightforward approach is the brute force method. Here, the idea is to evaluate every possible subarray, calculate its product, and determine whether the product is positive. If it is, we then track the length of that subarray and update the maximum length found so far. To implement this, we would iterate through all possible starting indices of subarrays, and for each starting index, iterate again through all possible ending indices. During this process, we would compute the product of the elements in each subarray to check its sign. While this approach is simple to understand and implement, it comes with a significant drawback. The nested iterations result in a time complexity of n², making it computationally expensive for large arrays. Additionally, it has a space complexity of 1, as no additional data structures are required. However, the repeated product calculations make this method inefficient and impractical, especially for arrays with sizes exceeding 1,000 elements. This trade-off between simplicity and performance highlights the need for a more efficient solution. Recognizing the limitations of the brute force approach, we can optimize the solution by dynamically tracking the product's sign as we traverse the array. The key observation here is that the product of a subarray is positive if it contains an even number of negative numbers. To take advantage of this, we maintain two state variables, POS_len, which tracks the maximum length of a subarray with a positive product ending at the current index, and neg_len, which tracks the maximum length of a subarray with a negative product ending at the current index. We initialize both variables to 0 and then iterate through the array. For each element, if it is positive, we increment POS_len by 1 and, if neg_len is non-zero, increment it as well. If the element is negative, we swap POS_len and neg_len, effectively flipping the product's sign, and then increment both lengths appropriately. Finally, if the element is 0, we reset both POS_len and neg_len to 0, as a 0 breaks the subarray. Throughout the traversal, we track the maximum value of POS_len, which gives us the desired result. This approach is highly efficient, operating in O and time since we make a single pass through the array, and it has a space complexity of O(1), relying only on two variables. The optimized approach relies on a few fundamental observations. First, multiplying by a positive number retains the product's sign. Second, multiplying by a negative number flips the product's sign, which is why swapping and updating POS_len and neg_len is critical when encountering a negative element. Lastly, encountering a 0 essentially resets the product, requiring us to restart the subarray tracking. These principles make this method robust and efficient. While this approach ensures correctness and linear time complexity, it does require careful handling of state transitions to avoid errors. Ultimately, the optimized approach was chosen for its scalability and ability to handle larger input sizes, unlike the brute force method, which is computationally prohibitive for arrays with thousands of elements. The key breakthrough was realizing that we don't need to calculate the product explicitly to determine its sign. Instead, dynamically tracking the lengths of subarrays with positive and negative products allows us to minimize computational overhead while still solving the problem correctly and efficiently. This makes the optimized strategy not only elegant but also highly practical for real-world constraints. To solve this problem using the brute force approach, we start by understanding the input and output. The input is an array of integers, which can include positive numbers, negative numbers, and zeros. Our goal is to determine the length of the longest subarray within this input array that yields a positive product when all its elements are multiplied together. To achieve this, we first initialize a variable max_length to 0, which will track the maximum length of such subarrays. Then, we use a nested loop structure to evaluate every possible subarray. The outer loop iterates through all possible starting indices of subarrays, while the inner loop iterates through all possible ending indices for each starting point. This setup ensures that we examine all potential subarrays in the array. Once we have the nested loop set up, the next step is to calculate the product for each subarray. For a given starting index I and ending index j, we compute the product of all elements in the subarray ARR, ij plus 1. To do this efficiently within the inner loop, we initialize a variable product to 1 at the start and then multiply it by each element in the subarray. After calculating the product, we check its sign. If the product is positive, we calculate the length of the subarray as j I plus 1 and update max_length to the maximum of its current value in this new length. In addition to these calculations, it's important to handle edge cases. For example, when the input array contains only zeros, the result should be 0 since no subarray can have a positive product. Similarly, for single-element arrays, if the element is positive, the result is 1, otherwise, it is 0. After processing all subarrays, we simply return max_length as the final result. The brute force approach works by explicitly evaluating every potential subarray to ensure no solution is overlooked. While this method is straightforward and guarantees correctness, it comes with significant limitations. The time complexity is O(n cubed) because of the nested loops and the additional computation required for the product of each subarray. This makes the approach impractical for large input sizes. However, its simplicity is a strength, as the algorithm is easy to implement and serves as a baseline for more efficient approaches. In terms of data structures, the algorithm only relies on the input array itself, directly accessing its elements during the nested loops. No additional data structures are required, making the implementation minimalistic but computationally expensive. This brute force solution involves three primary operations. First, the nested loops systematically iterate over all possible starting and ending indices of subarrays. Second, for each subarray, the product is calculated by sequentially multiplying its elements. Finally, the length of each subarray is computed as ji+1. While the approach is not optimized, there are potential improvements that can be made. For instance, instead of recalculating the product from scratch for each subarray, we could maintain a running product that gets updated as the subarray expands. Additionally, we can terminate early if the product becomes 0, as any further calculations for that subarray will not yield a positive product. These optimizations reduce redundant computations, though they don't eliminate the fundamental inefficiencies of the brute force approach. Analyzing the complexity of the brute force approach, its time complexity is O(n cubed). This comes from three factors: the outer loop runs n times, the inner loop runs up to n times for each iteration of the outer loop, and the product computation involves up to n multiplications for each subarray. While straightforward, this cubic time complexity severely limits the approach's scalability. On the other hand, the space complexity is O(1), as no additional data structures are used beyond a few variables for computation. This minimal space usage is a strength of the brute force approach, but the excessive time complexity remains its primary drawback. To better understand the brute force approach, let's walk through an example. Consider the input array 1, -2, -3, 4. We evaluate each subarray. For the subarray 1, the product is 1, which is positive, and its length is 1. For the subarray 1, -2, the product is -2, which is negative. For 1, -2, -3, the product becomes 6, which is positive, and its length is 3. We continue this process for all subarrays, ultimately finding that the longest subarray with a positive product is 1, -2, -3, so the result is 3. Now, consider an edge case. If the array is 0, 0, 0, all subarray products are 0 or undefined, so the result is 0. Another edge case is a single element array like -1. Since the product is negative, the result is 0. These examples illustrate how the brute force approach handles a variety of scenarios. This Python code defines the solution for LeetCode problem number 1567, maximum length of subarray with positive product. It employs a linear time algorithm to efficiently determine the maximum length of a contiguous subarray with a positive product. The solution utilizes two key variables, POS_len and neg_len, to track the lengths of the current subarrays with positive and negative products, respectively. It iterates through the input array nums while updating these variables based on the value of the current element. 1. Initialization, max_len is set to 0 to store the overall maximum length of a subarray with a positive product. POS_len and neg_len are initialized to 0. 2. Iteration, for each number in nums. If the number is positive, the POS_len is increment, and the neg_len is updated only if it was non-zero. If the number is negative, the roles of POS_len and neg_len are effectively swapped, as a negative number flips the product's sign. If the number is 0, both POS_len and neg_len are reset to 0, as 0 breaks any contiguous subarray. 3. Tracking maximum length. At each step, max_len is updated to the maximum of its current value in POS_len, which tracks the length of subarrays with a positive product. 4. Return result. Finally, max_len is returned as the result. The algorithm runs in O(n) time, where n is the length of the input array, as it processes each element exactly once. It also uses O(1) space, as only a few variables are maintained throughout the computation. This makes it an efficient solution for the problem, capable of handling large input sizes within the constraints. Here, we begin with the Java implementation for solving the problem of finding the maximum length of a subarray with a positive product. The method getMaxLen takes an integer array nums as input. We initialize three variables, maxlen to store the maximum length of subarrays with a positive product, and poslen and neglen to keep track of the current lengths of subarrays with positive and negative products respectively. Both poslen and neglen start at 0. As we iterate over the array, we handle three cases based on the value of the current number. If the number is positive, we extend the poslen by 1, as it contributes to maintaining a positive product. Simultaneously, if there's an existing subarray with a negative product, we extend neglen as well. On the other hand, if the number is negative, it flips the signs of the subarrays. We calculate a new poslen based on the existing neglen, if it's greater than 0, and update neglen based on the current poslen. Finally, if the number is 0, it resets both poslen and neglen to 0 because a 0 breaks the continuity of any subarray. Throughout the loop, we consistently update maxlen to ensure we are tracking the longest subarray with a positive product. The implementation concludes by returning the value of maxlen, which holds the length of the longest subarray with a positive product that we calculate during the iteration. This method uses a single traversal of the array, making it efficient with a time complexity of O(n). The approach effectively handles positive, negative, and 0 elements, leveraging the properties of multiplication to dynamically update the lengths of subarrays with positive and negative products. By maintaining and updating these lengths at each step, we ensure an optimal solution to the problem. This completes the Java implementation. In this example, we start with the input array nums equals 1, -2, -3, 4. Initially, all our variables are set to 0, max_len, pos_len, and neg_len. For the first number, 1, which is positive, we increment pos_len by 1, making it 1, while neg_len stays 0. We then update max_len to the maximum of its current value in pos_len, which results in max_len being updated to 1. Moving to the next number, -2, which is negative, we swap pos_len and neg_len. Since neg_len was 0, the new pos_len becomes 0, and the new neg_len becomes the previous pos_len plus 1, which is 2. Max_len remains 1 because the maximum of 1 and the updated pos_len, which is 0, is still 1. Now, we process the next number, -3, which is also negative. Again, we swap pos_len and neg_len. The new pos_len becomes the previous neg_len plus 1, which is 3, and the new neg_len becomes the previous pos_len plus 1, which is 1. This time, max_len is updated to 3 because it is the maximum of its current value, 1, and the updated pos_len, which is 3. Finally, for the last number in the array, 4, which is positive, we increment both pos_len and neg_len. Pos_len increases by 1 to become 4, and neg_len increases by 1 to become 2. Max_len is updated to 4, the maximum of 3 and the updated pos_len. The final state is max_len equals 4, pos_len equals 4, neg_len equals 2, and the output is 4. In this second example, nums equals 0, 1, -2, -3, 0, 4, -1. We start with all variables set to 0. The first number, 0, resets both pos_len and neg_len to 0, leaving max_len unchanged at 0. For the next number, 1, which is positive, we increment pos_len by 1, making it 1, while neg_len remains 0. Max_len is updated to 1, the maximum of 0 and the updated pos_len. For the next number, -2, which is negative, we swap pos_len and neg_len. Since neg_len was 0, the new pos_len becomes 0, and the new neg_len becomes the previous pos_len plus 1, which is 2. Max_len remains 1 because the maximum of 1 and the updated pos_len is still 1. Next, we process -3, another negative number. We swap pos_len and neg_len again. The new pos_len becomes the previous neg_len plus 1, which is 3, and the new neg_len becomes the previous pos_len plus 1, which is 1. Max_len is updated to 3, the maximum of its current value, 1, and the updated pos_len. For the next number, 0, we reset both pos_len and neg_len to 0. After that, we process 4, a positive number, which increments POS_len by 1, making it 1, while neg_len remains 0. Max_len remains 3, as the maximum of 3 in the updated POS_len is still 3. Finally, for -1, which is negative, we swap POS_len and neg_len. The new POS_len becomes the previous neg_len plus 1, which is 0, and the new neg_len becomes the previous POS_len plus 1, which is 2. Max_len remains unchanged at 3. The final state for this example is max_len equals 3, POS_len equals 0, neg_len equals 2, and the output is 3. Now, in the third example, nums equals -1, -2, -3, 0, 1. Again, we begin with all variables set to 0. For the first number, -1, which is negative, we swap POS_len and neg_len. Since POS_len was 0, the new POS_len remains 0, and the new neg_len becomes the previous POS_len plus 1, which is 1. Max_len remains 0 as the maximum of 0 and the updated POS_len is still 0. For the next number, -2, which is also negative, we swap POS_len and neg_len again. The new POS_len becomes the previous neg_len plus 1, which is 2, and the new neg_len becomes the previous POS_len plus 1, which is 1. Max_len is updated to 2, the maximum of 0 and the updated POS_len. For the next number, -3, another negative, we swap POS_len and neg_len once more. The new POS_len becomes the previous neg_len plus 1, which is 2, and the new neg_len becomes the previous POS_len plus 1, which is 3. Max_len remains 2 as the maximum of 2 when the updated POS_len is still 2. When we encounter 0, both POS_len and neg_len are reset to 0. Finally, for the last number, 1, which is positive, we increment POS_len by 1, making it 1, while neg_len remains 0. Max_len remains 2, as the maximum of 2 when the updated POS_len is still 2. The final state for this example is max_len equals 2, POS_len equals 1, neg_len equals 0, and the output is 2. To analyze the time complexity of this algorithm, let's start by noting that it iterates through the input array nums exactly once. The size of the array is denoted as n, and during this single traversal, the algorithm performs a constant amount of work for each element. For initialization, we set up 3 variables, max_len, POS_len, and neg_len. These are simple operations that take 1 time. During the iteration, the algorithm evaluates each element in nums and makes a constant number of checks and updates, such as comparisons, assignments, and calling the max function. Each of these operations is 1, and since we're only looping through the array once, the total work done is proportional to the size of the array. Finally, returning the result max_len at the end is also an 1 operation. Combining all of this, the dominant factor is the single traversal of the array, making the overall time complexity n. This is supported by the fact that there are no nested loops or recursive calls, ensuring the algorithm scales linearly with the size of the input. Now let's evaluate the space complexity of the algorithm. The space usage remains constant, regardless of the size of the input array. This is because the algorithm only uses a fixed number of variables, max_len, POS_len, and neg_len, along with a loop variable for iterating through the array. All of these require 1 space. Additionally, the input list nums is not modified or duplicated, so no extra storage is allocated for it. Importantly, the algorithm does not rely on any auxiliary data structures, such as additional arrays, stacks, or hash maps, to achieve its results. Because the memory usage does not grow with the size of the input, the space complexity of the algorithm is 1, making it very efficient in terms of memory. Let's compare this optimized solution to a brute force approach. If we were to solve the problem naively, we would generate all possible subarrays of the input array and compute the product of each to check if it's positive. For an array of length n, this would involve generating n² subarrays. Then, for each subarray, calculating its product would take k operations, where k is the length of the subarray. This results in a worst-case time complexity of O(n) cubed, which is computationally expensive for larger arrays. In contrast, the optimized solution avoids generating subarrays or explicitly computing their products. Instead, it dynamically tracks the lengths of subarrays with positive or negative products using simple integer variables. This drastically reduces the time complexity to O(n), because each element is processed exactly once, and the space complexity remains O(1), since no additional data structures are used. The efficiency gain here is significant, making the optimized approach far superior for handling larger inputs. Let's break down the performance of the optimized algorithm under different scenarios. In the best-case scenario, where all elements of the array are positive, the algorithm still performs O(n) operations because it needs to iterate through the entire array once. For the average case, with a random mix of positive, negative, and zero values, the algorithm still processes each element exactly once, maintaining O(n) complexity. Even in the worst-case scenario, where the array contains zeros and alternating signs, the algorithm continues to operate in O(n) time, as it only performs constant work for each element without revisiting any part of the array. In conclusion, the optimized algorithm outperforms the brute force approach in every respect, reducing the time complexity from O(n) cubed to O(n), and the space complexity from O(n) to O(1). By leveraging dynamic programming principles to track subarray lengths without explicitly storing or computing subarrays, the solution achieves both efficiency and elegance. When solving this problem, there are some common pitfalls that can trip you up if you're not careful. First, ignoring edge cases is a frequent mistake. For example, what happens if the input array is empty, has only one element, or is filled entirely with zeros? Failing to handle these scenarios can lead to unexpected failures. The solution here is to explicitly account for these edge cases in your implementation. Another issue arises when you assume that array elements are always positive. If your logic doesn't handle negative numbers or zeros properly, your results might be incorrect. Make sure your approach accounts for all possible values. Then there's the problem of using nested loops unnecessarily. While a brute force approach might seem straightforward, it often results in O(n) squared time complexity, which is inefficient for large inputs. Instead, optimize using techniques like sliding windows, prefix products, or dynamic programming to achieve linear time complexity. Lastly, be cautious about overflow errors in product calculations. In languages that don't handle large numbers well, this can crash your solution. Techniques like modular arithmetic or logarithmic transformations can help mitigate this issue. It's also important to ensure you fully understand the problem constraints. Misinterpreting these can lead to overcomplicating your solution or optimizing prematurely, which wastes time. Focus on building a correct solution first. You can optimize later. Now, in interviews, there are a few additional insights to keep in mind. Recognizing patterns is critical. Many array problems can be solved using sliding windows, prefix sums or products, or dynamic programming. Identifying the right approach early on can save you time. Also, prioritize edge cases during interviews. Don't hesitate to ask clarifying questions about special scenarios, like arrays containing zeros or negative numbers. This shows your attention to detail. Be ready to explain the trade-offs of your solution. For instance, why is your optimized approach better than brute force? Interviewers often want to see that you understand the real-world implications of your choices, especially when working with large datasets. Finally, if an in-place solution is required, be mindful of space complexity and avoid using unnecessary data structures. To deepen your understanding, it's helpful to explore related problems. For example, LeetCode 53, which involves finding the maximum subarray, relies on Cadon's algorithm, a technique that's highly relevant here. LeetCode 152, maximum product subarray, is another closely related problem, as it deals with products and sign changes. Similarly, LeetCode 560, subarray sum equals k, and LeetCode 238, product of array except self, both teach important concepts that can be applied to variations of this problem. Additionally, there are alternative approaches to consider. The sliding window technique is a powerful tool for solving contiguous subarray problems efficiently. However, it may require some workarounds to handle zeros or negative numbers properly. This approach typically runs in O(n) time but can get tricky with multiple pointers. Another option is using prefix products or sums. This approach simplifies range queries by pre-computing values, though it does require additional space for the prefix arrays. The trade-off here is between simpler logic and increased space usage, but the time complexity remains O(n). Finally, another approach worth mentioning is divide and conquer. This method can be particularly useful for problems like the maximum subarray, where the solution can be broken into smaller subproblems. However, it's not always the best option, as the complexity is typically O(n*log(n), which can be slower than more optimized O(n) techniques. For simpler variations of the problem, divide and conquer may be overkill. It's important to evaluate the specific requirements of the problem to determine if this approach is worth the added complexity. By understanding these methods and their trade-offs, you'll be better equipped to handle not just this problem, but a wide range of related challenges as well. Great job! To summarize, we tackled the problem by exploring both naive and optimized approaches, learning valuable lessons about handling subarrays and their properties. Remember to practice similar problems to reinforce these concepts. Thanks for watching, and don't forget to stay connected for more content. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!